Here's a claim that's too good to be true. You can take an engine built to do math on one number at a time, point at an entire grid of numbers instead, and it just works. Data box, no rewrites, nothing torn out. Today I find out if that's actually true or if I've been mistaken and accidentally lying to you this entire time. So today we're going to go from a scalar build into number, which is single numbers, and change that into tensors, which is grids of numbers. And the entire engine we've built so far is about to get put on trial. Does it survive the jump, or does the whole thing fall apart the second the data stops being a single number? Now, if you caught the first two episodes, you already know why I think it holds. This is the exact promise I made you back then, that none of the machinery, the graph, the closures, the backward pass would care what's actually flowing through it. And if you just showed up, welcome. You picked a great one to start on. Okay, so to start with, we needed to determine what even is a tensor, because the word sounds way scarier than the thing that it actually is. A tensor is just a grid of numbers. Example is a list is a one-dimensional tensor. A table that has rows and columns, that's a two-dimensional tensor. So you stack those, you get a three-dimensional, and that's it. It's numbers and a shape. But here's the part that actually matters for how we build it. And this is how real libraries such as NumPy and PyTorch and pretty much all of them do it under the hood. A tensor isn't stored as a grid, it's stored as one long flat list of numbers, one straight line. And then separately we keep a shape, like example would be 2 by 3. And the shape is just the lens. We read that flat line through. So the numbers are always one-dimensional in memory. The shape is the thing that tells us how to see them as a grid. And why do we do it that way instead of using something like a list of lists? Well, that would be because a flat buffer is fast, it's simple, and it makes everything later, such as reshaping or transposing, even the matrix math that's coming, way cleaner. So flat data plus a shape, that interprets it. Hold on to that, because that's the whole design. So let's build this out, and I want you to pay attention and see how much of this you already recognize from previously. So our node, I'm going to be calling it tensor data, carries the exact same four things our previous model node did. It's got its data, it has gradient and its children, the nodes it came from, and its backward closure. That little function that knows how to push gradient into its input. Same four roles, literally the same as episode 1. The primary difference, the two fields changed type. Back then, data was one F64 or one number. Now it's a vector F64 or a list or a list of flat numbers. And grad, same deal. It went from one number to a whole buffer, same length as the data. One gradient slot per number, and that's it. That's the change. Everything else is a straight copy and paste from the previous engine. Now we do have a new rule that we have to enforce, and this rule's very important. If a tensor is a flat buffer plus a shape, well, those two things have to agree. So if we say that a shape is 2 by 3, we better have exactly 6 numbers in the buffer. 2 times 3, not 5, not 7, it has to equal 6. So the rule is called the size invariant. And all it is the length of the data has to equal the product of the shape. You multiply the dimensions together, and that's how many numbers you need. And I enforce this right in the constructor. If they don't match, it panics on the spot, which means a broken tensor literally cannot exist in this system. You can't build one. Same idea as the scalars, where grad always started at 0. The constructor owns the rules. So every tensor is valid the moment it's born. So little detail I actually liked. An empty shape multiplies out to 1 because multiplying nothing together gives you 1, which correctly means a single scalar. The math just works out on its own. And what I actually do here is I split the constructor into two layers. One that does the actual validation, so it checks the sizes, sets up the zeroed gradient buffer, and the other just does the RC RefCell wrapping and hands off to the first one. So that wrapper can't skip the check, even if it wanted to. The rules live in exactly one place. Okay, so now for the actual operations, and these are going to go by fairly fast, because honestly, they're barely different from the versions we used previously. So you add two tensors the same shape, and we just add them number by number. Position 1 plus position 2, position 2 plus position 2, all the way down the line. Rust, the clean way to do this is the zip map collect pattern. You pair up two buffers, add each pair, collect the results into a new buffer. And the backward addition's derivative is 1. Remember, so it just passes the gradient straight through to both inputs, exactly like the previous version. You just do it per element now. So next what we'll do is we'll add the multiply function. It's the same structure. You'll multiply the two tensors number by number for the forward pass. The backward is the product rule from the last episode. Each input's gradient gets scaled by the other's input value. Just again, run element by element down the buffer. Same math, more numbers. So that implementation's really clean, right? Too clean, too easy. So the contract lifts, like I said it would, but getting Rust to actually compile it actually hit a wall here. Twice this session. I had two bugs, and here's what makes them worth showing you. They threw the exact same error, word for word, and they were completely different problems. So I'll walk you through both, because telling them apart taught me maybe the single most useful Rust debugging skill that I've picked up so far. Well, number one of the two errors, my multiplies backward function tried to write to both inputs gradients inside one loop. Grab the first input, borrow it mutably, add to its gradient, grab the second input, borrow it mutably, add to its gradient. Fine usually. Except remember our old friend from last episode, A times A, the reuse case? When you multiply a tensor by itself, first input, the second input are the same node, the same cell. So I'm trying to grab a mutable borrow of it, while I'm already holding a mutable borrow. And RefCell, which checks these rules at runtime, goes, nope, it errors out. Already mutable, it borrowed. And here's what actually got me. I'd already used the exact same, into locals trick from episode 1. Read the data out first to dodge a read-write clash, but it only fixed reads clashing with writes. This is two writes clashing with each other. Totally different problem. Same trick doesn't touch it. The fix was compute both gradient changes into separate local buffers first, no borrows held at all, and then apply them in two totally separate loops. So the two mutable borrows are never alive at the same time, ever, that it's got. And finally, number 2, and this one's particularly sneaky, is the error didn't even point at my multiplication function, it pointed at my test. When I called backward function in the test, now I wrote it like we'd seen earlier, borrow the node mutably, and then call its backward closure. Looks totally innocent, but here's the thing. That closure, when it runs, reaches back and reads its own output node. That output node, it's the exact same node I just borrowed mutably to make the call. So the closure tries to read it, just a normal borrow, while the call side is still holding the mutable borrow on it. So it creates the same collision, same exact error message, and the fix was tiny. The call site, I don't need a mutable borrow at all. I'm only reading the closure to call it, so just a normal borrow, not borrow mute, or borrow mut, or however you want to say that. And, that one word actually fixed it. Now, here's why I kept both of these in. Look at what just happened. Two completely different bugs. One was two writes fighting each other in a loop. The other was a read fighting a write. And over a totally different file, different causes, different fixes. And they printed identical error messages, already mutable, they're mutably borrowed. If you had only read the error text, you have no idea which of the two problems you even had. So how do you tell them apart? You read where the error points, not what it says, where it says it is. While 1 pointed inside the loop, while 2 pointed at the test call site. The location is the clue. The message is almost useless. And that's the skill. Same error, different causes. You read the location, and nobody teaches you that really in tutorials. So most tutorials edit out the part where the person's really confused. I'm trying to leave it in because the confusion itself is a lesson. So the moment of truth will run our tests. We have 6 of them. We have the valid tensor build that holds its shape. We have number 2, which is mismatched shape gets rejected, so the guard actually fires. 3, the wrapper wraps the validated node. 4 adds works gradient straight through. 5 multiplies works the crossover gradients. And 6 is the big one. It's the A times A, the reuse case. And the one that caused all the pain today. Gradient comes back as 2 times A, 6 and 8. So the exclamation holds and bar discipline holds on reuse. That's all 6 good. So that's the foundation. We've got tensors, they add, they multiply, and the gradients come back through both. The engine survived the jump from single numbers without a rewrite, exactly like I had promised 2 episodes back. But everything we did today is what's referred to as element-wise. Number 1 meets number 1, straight down the line, easy. Next episode's where it gets real. Matmul or Matmul matrix multiplication, and that's the first genuinely hard thing in this whole project for 2 reasons. Its forward pass isn't a simple loop anymore, it's an actual algorithm, and its backward is the first gradient that's matrix shaped, so it has transposes. You have to flip, or the matrices have to be flipped around. It's the whole thing. So that's the episode where the engine starts doing the math that actually powers the neural network. If you're building along with me, the code's in the description. There's a raw unedited version with the Code With Me series if you want to see the messy version of me just staring at an error for 10 minutes. So thanks for watching, and I'll catch you guys in the next one.
Late night in the sun again. City lights blur through the rain. Another alarm, another ghost in the system. Blue light glow from the dashboard pane. Seeing alerts falling down like rain. Everybody sleep while we stay awake, watching for the threats inside the waves. APT shadows moving slow through the dark. Tiny anomalies leave the mark. Dread hunters tracing patterns deep while the whole damn city asleep. CIA stuck inside my brain. Confidentiality washed away. Integrity break in a single night. Availability fading with the lights. Terminal glow in the apartment haze. Another overnight shift for days. Too many thoughts I never say. Just watching packet traces fade after the alerts. Still hearing static in my head. Neon lights outside the window, while the dashboard's glowing red. After the alerts, every long night changed me slow. Trying to find a hidden signals in a city full of gold. False positives mixed with fear. Trying to tell what's really here. Every packet got a story told. Some turn warm and some turn cold. Purple teams try and bridge the divide. Red and blue through the neon lights. Learning how attackers move before they break straight through. Rain slides slow down the window frame. Every shift starting feel the same. City in notes and tired eyes. Still watching patterns through the night. Everybody love the polished pose, never see what the burnout caused. Still I stay because it's real, trying to protect what people feel. Maybe the static means something, maybe the silence still talking, maybe the signal's never gone, just hidden somewhere in the storm. Gotta awake while the city's blurred, watching shadows through the static, trying to catch the hidden words after the alerts. Blue light cut through midnight rain, every long night builds awareness, every scar became the flame. Under the dashboard.